In this video, I want to introduce you to a concept called the mole. Now, the mole is probably one of the most important quantities in all of chemistry. And if you're going to move forward into our second semester for first year chemistry or use chemistry in AP chemistry, you're going to need to have a pretty good understanding of the mole. So I'm going to introduce you to the mole today and tell you about kind of the first round of what we're going to use it for. It's used in a lot of places throughout chemistry starting from this point forward. So you'll get used to hearing about it a lot and using it in various ways. So there's lots of different ways that we look at the mole in terms of it being a quantity. The way I want to tell you about it today is the mole in terms of what's called molar mass. The mole is known as basically a quantity of a substance that represents a certain number of atoms or molecules or particles. But the way we're going to look at it in this video and the way that we're going to use it first has to do with what we call molar mass. So 1 mole, and that's a quantity of a substance, 1 mole of a substance has a mass equal to its atomic mass or its molecular mass in grams. So we're going to use our periodic tables for this. If you don't have a periodic table close by, get one, pull yours out, and look at it as we start looking through some of these mole calculations. So the word mole itself, more or less, is kind of in the same category as, say, the word like a dozen, for example. A dozen means 12 of anything. And there's lots of other numbers or other words like that in our language that represent a quantity. So a dozen is probably the most common one that we see. Sometimes we hear words like gross. A gross means a dozen or 144 of something. And that could mean a gross of anything, a gross of eggs, a gross of pencils, a gross of cars. It could be anything. A mole is just like that. It's a word that means a specific quantity. And what that quantity is varies depending on how exactly you're using it, but it means a specific number of atoms, molecules, or particles as we look at substances in chemistry and in chemical reactions. For today, we're not going to actually use that quantity so much as we're going to look at what's known as molar mass. So for us, we're looking at the grams part of it, or the molar mass part of it, the mass of 1 mole. So if you look at your periodic table, a mole of sulfur, 1 mole of sulfur will have a mass in grams that we can go in the lab and actually look up. If I pull up our periodic table here, pardon me, if I pull up our periodic table here and look at sulfur on the periodic table here, you can see that sulfur has a molar mass or an atomic mass, this red number on this particular periodic table, 32.066. That mass that we used back in the beginning of the year to talk about the average mass of 1 sulfur atom also represents the molar mass of the element sulfur. So if we're looking at an element like sulfur and we're going to look at its molar mass is 32.066 grams. 1 mole of sulfur is 32.066 grams of sulfur. So on the periodic table, I just look at the element sulfur, I pull that red number off of there, and I use it as the molar mass of the substance. Another example, mole of lead. Lead's another element off of our periodic table. So if I jump over to my periodic table and slide over here to lead, it's listed as 207.2. That's the average mass of 1 lead atom. But for our purposes here, we're looking at 1 mole of lead atoms. And 1 mole of lead atoms has a mass of 207.2 grams. So as we look at 207.2, it can be the mass of 1 atom in 207.2 AMUs, way back in, say, the fall. But now that we're getting into second semester and actually working with these elements in a larger scale in our reactions, 1 mole of lead atoms has a mass of 207.2 grams of lead. Why we need the mole is pretty simple. We can't go to the lab and measure out, count out, use 1 atom of lead or 2 atoms of lead. Because 1, you can't see atoms, they're always too small. 2, you couldn't get a mass of lead atoms and actually use individual lead atoms separately and be able to keep track of how they're reacting, how much of them have reacted and how much of them haven't. So we use a larger quantity to kind of get it up to a scale we can actually see. And when we measure out 207 grams of lead from a jug or a bottle or container from the stockroom, we could mass out 207.2 grams rather easily for lead. We could mass out 32.066 grams of sulfur rather easily. So the quantity, the mole, lets us get to an amount of a substance that's relatively usable. That's something we could actually go in the lab and measure out. And so our calculations and our work with the mole will be using those quantities that are a little bit more realistic for us to actually get used to seeing in the lab. Now, what about a substance like water that we're going to see in a lot of reactions, that we see in a lot of things that we do in chemistry? 1 mole of water includes hydrogens and oxygens. In fact, specifically, a hydrogen, another hydrogen, and an oxygen. 2 hydrogens and 1 oxygen, essentially. So to figure out the mass of that, I need to go to my periodic table once again, look at hydrogen's mass. So you'll check out the top corner of my periodic table for hydrogen. And on this version, it's listed as 1.00795. Now I might round it off just a little bit and say 1.008, something like that. But that's the mass of my hydrogen, and I'm going to need 2 of those. On the other corner, the oxygen's mass is 15.9994, right around 16. So hydrogen's about 1.008, oxygen's about 16. If I was to add that all together, okay, it's the total of 2 hydrogens and 1 oxygen. So oxygen's about 16, hydrogen's about 1, so 2 hydrogens and 1 oxygen makes about 18 if I add that up in my calculator. 2 hydrogen masses from the periodic table, 1 oxygen mass from the periodic table. One more example would be this. This is magnesium nitrate, and I've gone ahead and just shown you the whole thing kind of pulled apart here. Magnesium nitrate is magnesium, nitrogen, and oxygen. And more specifically, as you see here, it's 1 magnesium atom, 2 nitrogens, and 6 oxygens. Now that adds up to about 148.31. If you're not quite sure how I figured that out, let's take a look at calculations for that real quickly, and I'll show you kind of what we're looking for there. Go to my periodic table. Magnesium's mass is around, Go to my periodic table, and magnesium's mass is around 24.3 or so. Okay. So if I put that down as about 24.3 grams, that's magnesium. Okay. Nitrogen's about 14, and I need 2 of those. So 2 times the mass of nitrogen, which is around 14. And 6 times the mass of oxygen, which is around 16. So I add all this together. One magnesium is 24. 2 nitrogens that are each worth 14. So that's another 28. And then 6 oxygens that are worth 16 apiece. That's 96 for just the oxygens. And if we add all that up, we get about 148.3. Now you'll see sometimes variations like, why is there a 1 here? Well, if we look closely, magnesium is about 24.31. So if we add it up to about 2 decimal places, we come out somewhere pretty close to about 148.3. So magnesium nitrate would consist of magnesium, nitrogen, and oxygen. And we have to be careful, especially when there's parentheses, to count the atoms correctly, just like we would when we're balancing an equation or using it in something like that when we're studying just reactions in general. So what I want you to do with me here is jump over to the worksheet that you should have, hopefully. And if you don't, these are just some other examples that you can follow along with us on, and go ahead and just jot down a few more examples into your notes or whatever you happen to be using to keep track of what we're doing today. So on this page, Molar Mass Practice page, we've got a whole bunch of compounds, and all you're being asked to do here essentially is calculate the molar mass, how many grams are in 1 mole of each substance. So you just need to go to your periodic table and add these up. I'm just going to run through a number of examples with you here so that you've got a few more examples in your pocket as we get started. So go to your periodic table, make sure you have that in front of you, and let's try a few of these. All right, the first one, number 1 on here, silver chloride, AgCl. So I go to my periodic table, I'm going to look at silver right here at element 47, and the mass is 107.868. All right, so for silver chloride, I need about 107.868. All right, and then for chlorine, go back to my periodic table again, and chlorine's mass is 35.453. Okay, so 35.453. And then I just need to add those together. So pull out your calculator and punch that in, add that up. Make sure you're punching these into your calculator, especially as you get into some more complicated ones, and make sure that you get some of the answers that you see in me get. If I punch that in and add that up, I get a mass of about 143.321. Now that's very precise. I'm comfortable with your molar masses here having 2 decimal places, so even 143.32 would be okay. We want to label everything in grams because all of these are molar masses in 1 mole. How many grams in 1 mole? And so label this with grams at the end, and this would be grams per mole, essentially. All right, let's do another example. Let's look at number 2. This is another gold nitrate, gold 3 nitrate. So I need gold's molar mass. Go back to my periodic table again. And here's gold, 196.967. It's a pretty heavy atom. 196.967. Okay. And then I need nitrogen. Now, how many nitrogens have I got? 3 NO3s. That means 3 nitrogens and 9 oxygens. Right? So 3 nitrogens. I need 3, let's see here. Nitrogen's mass again was around 14. So 14.0067. I'm going to go ahead and round that off to 2 decimal places, 14.01, and use it as that, because that's probably precise enough for almost anything we would do. Now I also need 9 oxygens. And again, if I go to my periodic table, remember this is 3 times 3, so 9 oxygens. Go back to my periodic table here, and oxygen's mass, 15.9994. Let's call that, we're going to go ahead and call it 16. For the purposes of our work here, we're going to go ahead and call this a mass of 16, okay, for oxygen. At all times throughout the year, you can go ahead and use that number. Now, we need to add this up. 196.967 plus 3 nitrogens, 3 times 14.01, plus 9 oxygens, which are each 16. That's going to be a pretty big total. Let's go ahead and add that up. Take a moment with your calculator and punch those in, and pause me and see if you get the answer that I get here in a moment. Now, hopefully, if you punched that in your calculator and found it for yourself, you got an answer right around 383. So a pretty big mass, 383, 382.997, 382.997 grams. And again, I would say 383.00 would be okay, but that would be about the most precise we'd need to be. Two decimal places, maybe 3 is all you'll ever need on adding these up. So that's a bunch of atoms all put together and a pretty heavy molar mass. Some of these can range in the hundreds, as you're starting to see. Some of them will be quite a bit smaller, and not all of them involve quite this many atoms. So let's look at one that's a little bit simpler. Okay, go down here to number 9. Number 9 says simply, what is the molar mass of calcium? So remember, when we're looking with just a plain element, it's relatively simple. You just go to the periodic table, and for like something like number 9, calcium, you just look up calcium's mass, and you're done. Nothing to add up or anything, because it's just a single calcium atom. So for calcium, 40.078, and I'm all set. That's all I need to have. 40.078 grams of calcium in 1 mole, and you're all done. One more example. Let's look at number 5, C2h4 O2. So a couple different elements, 3 elements here, and nothing too major, so this shouldn't be too tough, but we want 2 carbons. Go back to my periodic table again and find carbon's mass is 12.01. And again, we'll go ahead to 2 decimal places most of the time, so carbon at 12.01. And I need 2 of them, so 2 times 12.01. 4 hydrogens. So back over to the other side again is hydrogen at 0.08, pardon me. So for hydrogen, we need 4 of those. 4 times 1.008. And then 2 oxygens, and those were each 16, if I remember correctly. So 2 times 16 for oxygen. Some of these atoms you'll use elements you'll use so often, you just kind of get to know their masses by heart. If I go ahead and add that up, what's my total going to be? Take a second, punch that in, make sure you get the same answer. If you punch that in, hopefully you get somewhere around 60. This comes out to be about 60.05. So 60 grams or so per mole for C2h4 O2. Now, even if we don't know what all these substances are by name, we can look up and rather easily calculate their molar masses. It doesn't take very much at all to punch them in the periodic table and get a molar mass for any substance out there. The more atoms there are, the more complicated it might get, or the more you have to keep track of everything that you're doing. So with those 4 examples here and the others that we did back on the slide over here, with those examples sort of in your hand, what I'd like you to do is work on the rest of this page. Now, if you're doing this as homework and you're outside of class, then go ahead and work as far as you can on the rest of the page, and don't dodge the difficult ones. Make sure to work on some of the bigger looking ones with parentheses or lots of atoms like number 8, or lots of different elements like number 38 where there's lots of variety. But don't steer around those tough ones just because they look a little more challenging, because you're going to have to be able to do those. If you are working on this as an assignment while in class, then maybe you have other instructions as far as how far you should go before maybe you check your work against the answer key and see how you're doing. If you make a mistake, try to retype it in your calculator. If you find that the answer key doesn't match your work, punch it back into your calculator and see if maybe it was just a bad keystroke, which happens sometimes. And double checking your math on these is always a good idea anyway. So go ahead with either finishing the rest of this page or whatever assignment you've gotten from me in class, and we'll take it from there the next time we have a chance to get together on this.